All right, number one on your study guide, y equals cotangent of x plus cosecant of x over cosecant of x. If we just look at this as the problem it is, without considering any kind of trigonometric identities, let me just do this, and I'll leave myself a little bit of room over here. It's a quotient structure, so the quotient will be necessary to differentiate. So if I do y prime equals, I have to do low d high, which is going to be cosecant of x. D high is going to be the derivative of cotangent, which is negative cosecant squared x, plus the derivative of cosecant of x, which is going to be minus cosecant of x cotangent of x, minus high d low, which is going to be minus cotangent of x, plus cosecant of x, times the derivative of cosecant, which is negative cosecant of x, cotangent of x. All that goes over cosecant squared of x. Square over the square of what's below. So low d high minus high d low over the square of what's below. The d high is a binomial, the high is a binomial, so parentheses necessary on both of those. I didn't necessarily need parentheses here, but I'm multiplying by negatives, so just to make sure there's no confusion there as to what I'm multiplying by. At this point, I would then distribute and simplify as much as possible. That cosecant goes through all of that, and this minus minus makes a plus plus, and we can distribute this here, like so. That gets me y prime equals negative cosecant cubed x minus cosecant squared x cotangent of x plus cosecant of x cotangent squared of x, and then plus cosecant squared x cotangent of x, all over cosecant squared of x. We'll see that this is the same as that. They cancel because they're opposite signs. And the last thing I'd probably do here is I'd factor out a cosecant of x from everything. So y prime equals, so if I take the cosecant of x out, I'm left with negative cosecant squared plus cotangent squared all over cosecant squared. That cancels that down to a cosecant. And cotangent squared minus cosecant squared is equal to -1, I believe, if I remember my trig identities properly. If I just start with the sine squared plus cosine squared equals 1. Divide everything by sine squared, it gives me 1 plus cosecant squared x equals, that's not cotangent squared x, equals cosecant squared x. So if we move the cotangent, you have to be -1. So y prime simply equals -1 over cosecant of x. And that just, cosecant's 1 over sine, so y prime equals -1 over 1 over sine of x. So the answer is negative sine of x. That will be a way to do it. We'll call that the way we don't want to do. The one on the test should work similarly to this. If we focus on our top 4 trig identities, ones that change tangent, cotangent, secant, cosecant into sine and cosine structure, our original problem is y equals cotangent of x, which is sine of x over, cotangent's cosine of x over sine of x, plus cosecant, which is 1 over sine of x, all over cosecant, which is 1 over sine of x. Okay. We make it look a little uglier to begin with the intention of making it look prettier. Everything has a sine of x on it, so if I multiply everything by sine of x, this, and this by sine of x, I'm left with cosine of x plus 1. And if y equals cosine of x plus 1, y prime is negative sine of x. Okay. They get the same answer, but it's so much more difficult to try it without changing it to sine cosine structure. One on the test will be similarly done. If you can change everything to sine cosine structure, the simplified version you can get of your equation will differentiate very, very easily. If you go through all this, I mean, you give me the right answer, fine, I'll expect to get all the way to this nice, pretty answer, not leaving me here. All right, so you won't get full credit if you don't get me down to the simplest answer possible on that one. But again, number one on the quiz, trig identity sheet will help, and I would expect you to be able to transform what you have into something very, very basic that's very easy to differentiate. Number two, find the equation of tangent line to y equals 3 cosine of x. So here's my equation, and the point of tangency is pi over 6, 3 squared root of 3 over 2. That's an exact point of tangency. We'll see if we want to keep it that way or not, depending on what happens with the derivative. So y prime, the derivative of cosine of x is negative sine of x being multiplied by 3, so negative 3 sine of x. And I do want to caution you about the product rule. 3 is being multiplied by cosine of x, so some of you might be thinking, hey, maybe we have to use the product rule here. 3 is a constant multiple, so it's not going to factor into the derivative. So just bring your constant down, differentiate whatever the x expression is, stick them together to differentiate. So negative 3 sine of x, so the slope of my tangent line, which is what I'm looking for, I just have to do negative 3 sine of pi over 6. And of course, sine of pi over 6 equals a half. So negative 3 times a half is negative 3 halves. Okay, that's a pretty reasonable slope to work with, so I'm going to go ahead and keep everything exact. So this is y, this is x, that's m, y equals mx plus b gets me 3 times the square root of 3 over 2 equals m negative 3 halves times x pi over 6. Plus b. That cancels that down to a 1 and a 2, so 3 times the square root of 3 over 2 equals negative pi over 4 plus b. If I move the pi over 4 to the other side, I get a common denominator. This is 6 times the square root of 3 over 4 plus pi over 4. So b ends up equaling 6 times the square root of 3 plus pi all over 4. Slope negative 3 halves, y-intercept that, so y equals negative 3 halves x plus 6 square root of 3 plus pi all over 4. I would much prefer an exact answer to a approximate answer. I think you guys can all handle that, so expect to get to that point on the test. Number 3, differentiate the 4th root of 3 plus x squared. Anytime I see this word and I see a radical structure, I want to change it into a fractional power structure. Keep in mind, be cautious of a polynomial, a binomial or more here. 3 plus x squared is all to the first power. A lot of times people see that 2 and they think 2/4, but it's actually, it's going to be y equals parentheses 3 plus x squared to the 1/4 power. So be careful with changing to fractional power, that if multiple terms are in here, that entire expression is going to be raised to the first power, unless otherwise stated, in which case then you take that power 1 divided by that power 4, the root 4. So it creates a nice polynomial, or I should say a a power structure. So we have something to a power, so I'm going to use the power rule for differentiation. So y prime is going to be 1/4 the power times the base, 3 plus x squared, to one lesser power, 1/4 minus 1 is negative 3/4. Then I multiply that times the derivative of 3 plus x squared, which is 2x. That's a basic function there, so I'm done differentiating by the chain rule at this point. What's left to do is to simplify as much as possible. This 2 on top, that 4 on bottom reduce each other out, so that 2 becomes a 1, the 4 becomes a 2. 3 plus x squared, negative 3/4 belongs on the bottom, so my best final answer will be x on top, 2 times 3 plus x squared to the 3/4 power on the bottom. If I want to leave it in fractional power form. The other option for a good final answer here, y prime equals x on top, 2 times the 4th root of, and then I would do 3 plus x squared cubed. So if I want to change that fractional power back into a radical structure, the power 3 goes here, so the whole object to the 3rd power, the root 4 goes there. Either one of those answers would be acceptable as a good final answer in my opinion. Number 4, differentiate f of x equals 3x cubed minus 7x to the fifth. Exactly the same kind of problem as the last one. There's just no fractional powers happening. Once again, we have a object, 3x cubed minus 7x. It's not just x, it's a function of x raised to the fifth power. So again, it's a power structure. So if I'm going to differentiate f prime of x equals, I take my power, which is 5, multiply by the base, 3x cubed minus 7x, and reduce that to the fourth. And then the base has a derivative of 9x squared minus 7. Also differentiating that by the power rule. 3 times 3 is 9, drop the power by 1. 1 times 7 is negative 7, drop the power, you get x to the 0, so it goes away. So that is the derivative. So again, I've done a derivative here of f changed to f prime. And now to simplify, to make it as pretty as possible, 5 and 9x squared minus 7 are just a basic number times a parentheses structure, so I can do a distributive property there. I got my 3x cubed minus 7x to the fourth power. I'm going to leave as is. So my best final answer, in my opinion, would be parentheses 45x squared minus 35. Product of those two things by the distributive property. That's still being multiplied by 3x cubed minus 7x all to the fourth. I'm continuing to keep this in parentheses because I'm multiplying this whole product times this whole thing too. So if I don't put the parentheses around the 45x squared minus 35, I'm actually changing the structure of the problem. So do multiply those out, but do also keep it in parentheses there. Number 5, y equals 6 cosecant of 4x. Once again, this is a chain rule situation. This is a cosecant function, so I have to do the derivative of the cosecant. But the argument is not x, it's 4x. So there's going to be a chain of derivatives happening here in order to differentiate. Once again, I have a constant multiple of 6. That 6 is not going to do anything to the problem whatsoever. It's just going to come along. So I'm just immediately going to go straight to the derivative of cosecant. So I'm differentiating right away. So y prime equals 6 is a constant multiple. Nothing happens to it. The derivative of cosecant of anything is negative cosecant of that thing times cotangent of that thing. And the derivative of 4x is times 4. Even though it happens twice, it's only happening once in the original problem. Just one derivative of that goes outside. And once again, looking at what we have here, this times this times this. As far as simplifying concerned, of course, I'm going to put the minus in front. 6 and 4 make 24. So I'm going to multiply this times this, stick a minus in front. So y prime is negative 24 cosecant of 4x cotangent of 4x. Do make sure anytime you differentiate a trig function that you keep the argument the same. So cosecant of whatever, negative cosecant of that same whatever, cotangent of that same whatever. It was sine of 15x, it would be cosine of 15x, and then times the derivative of 15x. So make sure that the argument just keeps on coming down all the way through the problem. Number 6, differentiate g of x equals 4x plus 1 to the 7th times x squared plus 3x plus 1 to the 9th. This basic structure will be there on the quiz for number 6 also. This is a product rule. So I have function 1 being multiplied by function 2. So the product rule of differentiation is required to differentiate this thing. And then there's some specific things I can do to make it prettier, and we'll do all that stuff. Its current form is the best form to differentiate, so I'm ready to go right away. So once again, I'm doing calculus immediately. G of x changed to g prime of x. I'm allowing myself a lot of room because this is going to take up a lot of space. If I do the product rule, that's 1 d2 plus 2 d1. It's always the product rule. Product of functions of x, that's how you have to differentiate it. So if I do 1, that means write down function 1 as it is. So 4x, I have to write it right, 4x plus 1 to the 7th power. So function 1 stays exactly as it is. d2, I've got a object to a power, so I have to use the power rule along with the chain rule. So 9 is the power, comes down in front. X squared plus 3x plus 1 stays the base, which is now to the 8th power. And then the derivative of x squared plus 3x plus 1 is 2x plus 3. That was just 1d2. Something some students do wrong here is they've written down so much already that's got to be it. All I've done so far is this much. So I still got to do 2d1. So when I do 2, that's going to be function 2 exactly as it is. Here's function 2, x squared plus 3x plus 1 to the 9th. That's going to be multiplied by d1, which is going to be times 7 times 4x plus 1 to the 6th times 4. So this part here, 2d1. So 2d1, 1d2, and there's the entire product rule done. Now, what I told you in class and your homework with involving structures of this variety is you can always expect something to happen to simplify this, to make it easier to simplify this. And what that is you can anticipate this to 1 lesser power and this to 1 lesser power being the least or the greatest common factor of this entire expression here. So this thing underlined in red is one whole term. What's underlined in blue is one whole term. And if you take a look, 4x plus 1 to the 6th belongs to both of them. This has an extra one. X squared plus 3x plus 1 to the 8th happens to both of them. This has an extra one. So again, both of those guys to 1 lesser power is going to be a common factor. I'm going to expect you to do this step to make this as simplified as possible. So 4x plus 1 to the 6th times x squared plus 3x plus 1 to the 8th are being taken out. And what's left over, I'm going to do what's left over from this term in red. All right, so I'm taking 4x plus 1 to the 6th out, so 4x plus 1 to the 7th reduces by 6, so we're left with 4x plus 1 to the 1st. Nothing's happening to 9. X squared plus 3x plus 1 to the 8th is being taken out completely, so that's gone. And then times 2x plus 3. Then my plus sign happens. And the second parentheses, or the second group, I'm going to do this in blue, what's happened left with that. So x squared plus 3x plus 1 to the 9th, we're taking 8 of those out, so we're left with 1. X squared plus 3x plus 1. We're not messing with the 7, we're taking all 6 of the 4x plus 1 to the 6th out completely, and then times 4. And that gets me the contents of the bracket. What's left to do now, the black is done. I can make the red and the blue simpler by doing some algebra to simplify those. I personally don't write this down as I do all this stuff. I'm just going to work this out. For me personally, I like to multiply the binomials first. 4x times 2x is 8x squared. 12x plus 2x is 14x. 1 times 3 is 3. That's just FOIL. The outside and inside products add together, 12x and 2x, so I'm just going ahead and expect that. Here, of course, it's 28 times all that stuff, so plus 28 times all that stuff. Distribute the 9, I'm going to get 72x squared plus 126x plus 27 plus, and then 28x squared plus 84x plus 28. And finally combining like terms. So now that's the last step of all that. So I'm going to come back over here, go g prime of x equals, I'm going to bring all this stuff down, 4x plus 1 to the 6th times x squared plus 3x plus 1 to the 8th times 72x squared plus 28x squared makes 100 and, or just 100x squared. 126x and 84x makes 210x. And 27 plus 28 makes 55. And that would be the answer I'd expect to see on your paper for a problem of that variety. Simplified down as much as possible. Again, once you take out these powers, again, one less power than both of those, you should be left with a pretty basic multiplication of polynomials, addition of polynomials type problem here that is going to simplify down as much as possible. Number 7, we have a quotient inside a power structure. So f of y is a object raised to a power, so the overall structure of this problem is a power function. So we're going to do the power rule to differentiate. I can't make it any simpler than what it is, so I'm going to immediately go to f prime of y equals. And if I do the power rule, I'm supposed to take the power, which is 9, multiply by the same base to 1 lesser power, 8. And then I'm supposed to multiply by the derivative of the contents of the parentheses. The contents of the parentheses is a quotient, so I have to use the quotient rule to differentiate that. So here's the contents of the parentheses right here. And I'm going to use the quotient rule to differentiate that. So, low is more than one thing, so I put parentheses around it, d high times 1. Minus high, more than one thing, parentheses go around it, d low times 1, over the square of what's below, y plus 2, the quantity squared. So that'd be step 1 of this problem. Simply differentiate it to the extent you can. Y plus 1 over y plus 2 is a basic quotient rule level problem, so I did a derivative of it, so that's done. Step 2, the simplification step of this, I want to do exactly what I'm about to do here when I'm simplifying this, to make the easiest simplification possible, to make the most elegant looking answer possible. 9 is currently over 1, just creating numerator and denominator structures here. Y plus 1 over y plus 2 to the 8th is the same as a fraction of y plus 1 to the 8th on top and y plus 2 to the 8th on the bottom. Oops. For the green, y plus 2 times 1 makes y plus 2. Y plus 1 times 1 makes y plus 1, but that's being subtracted. All right, so if I'm simplifying the green as much as possible, I'm going to get y minus y makes 0, 2 minus 1 makes 1 on top, and then y plus 2, the quantity squared on the bottom. The final step here to make the best, again, most elegant answer possible, everything on top is 9 times y plus 1 to the 8th times 1, which is 9 times y plus 1 to the 8th. On the bottom, 1 times y plus 2 to the 8th times y plus 2 to the 2nd. These are the same basis, so I add the powers. So that right there would be the best answer possible to this problem. I would expect you to get down to this level on this answer. So make sure that you go through all those steps. It'll be the same basic structure. I'm going to change up these things, probably the power too, but that's how the problem should work on your test. What you're looking for in a good final answer, if you want to verify that you did things correctly, whatever this power is, it should be 1 less on top and 1 more on the bottom, and then there's some number being multiplied by it, is what typically happens on those. Number 8. Find dy over dx if x squared plus xy squared plus 5y cubed equals 7. So we have this implicit function that we're supposed to differentiate. I can't see any really easy way to solve for y, so to change it to an explicit function is out of the question here. So implicit differentiation is probably the best technique to be used. Structure-wise, a power function is as easy as anything, so I'm good with that. I'm also good with that. Here I have a product, so it's a product rule necessary for that. So looking at 3 different pieces, and of course 7's derivative is 0, so actually 4 different pieces. So piece 1, power rule. Piece 2, product rule. Piece 3, power rule. Piece 4, the answer is 0. So those are my 4 pieces, and if I differentiate each one individually, the derivative of x squared is 2x. I'm differentiating x, so nothing else necessary on that. Piece 2 has a plus in front of it. If it had a minus in front of it, you might even want to put a product rule in parentheses, because you do create from one object 2 objects, so the plus isn't going to make anything weird happen, but if it was minus, it would have to distribute, but I don't think I'll do that to be on the test. Function 1 is x, function 2 is y, and again it's 1d2 plus 2d1 is our product rule. So 1x d2 is 2y dy over dx. Since I'm differentiating a y expression, I put the dy dx on it. Plus 2d1 plus function 2, y squared exactly as it is. d1 is just the derivative of x, which is 1. I'm differentiating x, so nothing goes attached to it. All right, so that's done. And then derivative of 5y cubed is 15y squared, but we differentiated y, so we have to put a dy dx on it. And the derivative of 7 is 0. All right, so job 1, differentiate everything correctly. And again, if your derivative is of a y function, dy dx goes on it. If it isn't, you just simply do the derivative. So here's a y function, there's this derivative dy dx. Here's an x function, there's this derivative, no dy dx. X function, no dy dx. Y function, dy dx. Next step is to simplify. I can make this a little prettier here, so I'm going to do that. So 2x is fine. X times 2y times dy dx altogether makes 2xy dy dx. plus y squared times 1 is just plus y squared. All that's being added. Again, if this was a minus sign, this is a minus sign, that's negative, and that's also negative. 15y squared dy dx, can't make that any prettier. Okay, and once you get the problem as pretty as possible, there's no parentheses, just a bunch of terms. Some of the terms contain dy over dx. And some of the terms don't. Okay, I need to separate those, so I'm going to keep the dy dx terms right where they're at. I'm going to move the two blue highlighted, 2x and y squared, over to the right. So what's going to happen on the right-hand side is going to be equals negative 2x minus y squared. Just basic algebra, you move something across the equal sign, you change its sign. What's going to happen on the left-hand side is I have a common factor of dy dx. And I simply put 2xy plus 15y squared times dy over dx. And now I've got something times what I care about equals something else. And anytime I get this structure in algebra, something times what I want equals something else, I divide by the something being multiplied by what I want. So divide by 2xy plus 15y squared on this side. Divide by 2xy plus 15y squared on the other side, dividing both sides by the same object. This cancels this, leaving me with what I care about. Dy over dx equals the answer. Okay, you should expect on the test number 8, it'll be an implicit differentiation problem. Power rule and product rule of differentiation will show up. And again, from this point forward, it's just a matter of doing good algebra. Simplify really nicely, group together things that have what you care about and what don't have what you care about. Factor that what you care about out, divide by the coefficient of that. Number 9, once again, it looks like an implicit function is going on here. X squared y equals sine of x squared y. And it doesn't have to say the exact same thing, but this is a product of functions, so this is the product rule. This is a sine function, that's the sine rule, but it's also a sine of stuff, so it's a chain rule. So I've got a product rule, the derivative of sine of something, and then the chain rule going on here. And we're supposed to do dy dx. There's no easy way to get y equals, so we have to do it implicitly. So if I do the product rule for this blue circled one here, I'm going to get 1, that's function 1, and there's function 2. If I do 1d2, I'm going to get x squared. The derivative of y is 1, but then I have to put a dy dx because I'm differentiating y. Plus 2d1 is going to be plus y, which is exactly as it is, times the derivative of x squared, which is 2x. I'm differentiating an x expression, I get the derivative, that is what it is. Over here on the other side, I've got sine of x squared y. First of all, I differentiate the original structure of the piece, which is a sine function. The derivative of sine is cosine of the same thing, so cosine of x squared y. At this point, I don't put dy dx's on it. I don't do that until I get to the most basic function. So the derivative of sine is cosine of the same thing, but then the derivative of the argument is going to be the derivative of x squared y, which is going to be, if this is function 1 and this is function 2, since it's a product, x squared times 1 dy dx, 1 d2, differentiating y, so dy dx is necessary, plus 2, which is y, d1, which is going to be 2x. These are exactly the same because these are exactly the same. So whether that's going to happen exactly that way on the test or not, we'll see. But if it is, just know that you've already differentiated that. You just copy it all down again. Once again, that's the derivative. I've done the calculus part of it. Now I've got to do some algebra. All I can do to make this any prettier is just combine it together, get x squared dy dx. And this will be 2xy. I always like numbers in front. I like alphabetical order. What's happening here is I've got cosine of x squared y. This is one whole object being multiplied by this and by this. So a distributive property is going on. So if I look at this first multiplication, this x squared y is protected. So cosine of x squared y, all this red stuff is together as one thing. There's no distributive property going on in there. But this whole thing is being multiplied by this whole thing. One object times one object times one object times one object. Everything's just single objects being multiplied. So I'm going to put x squared in front. cosine parentheses x squared y, and then dy dx. Same deal here, I got this whole thing times this whole thing, single object times single object. All I can do is put the 2xy out in front of cosine, is going to get plus 2xy cosine of x squared y. So now it's simplified. Next job is to solve. I'm going to move the x squared cosine of x squared y dy dx over to the left. Move the 2xy over to the right. So if I do that, I get parentheses x squared, which is already here, attached to dy dx. I'm moving in x squared cosine of x squared y over to the left. And this whole thing, this is a dy dx, this is a dy dx, so we need a dy dx attached to that. I'm going to move the 2xy over to that side, so I already have a 2xy cosine of x squared y. And I'm moving a 2xy over, so minus 2xy is moving over. And all this stuff to do then is to divide by that stuff. So dy dx is equal to all this stuff divided by all this stuff. One thing I'm noticing, well, let me just write this down first. 2xy cosine of x squared y minus 2xy, and x squared minus x squared cosine of x squared y. Right? I'm going to put two terms on top and bottom. Again, that's the right answer. I wouldn't actually count that wrong. But I do challenge you guys to try and simplify things beyond what you see. So if we just put a circle around that, we're good. If you take a look at the top, if I factor out a 2xy, there's a bracket here, it's a little more easy to look at. And then on the bottom, looking at what I have here, if I take an x squared out, I'm going to be left with a 1 and a cosine of x squared y, the same two things as this with wrong signs. So I'm actually going to take a negative x squared out of that one. So it makes this one become positive. We'll put that front, cosine of x squared y. And then minus 1. Those cancel. And if I simplify as much as I can at this point, dy over dx is just going to be negative 2y over x. And considering that we're currently in the higher order derivatives chapter, imagine we had to take a second derivative of this or this. Hopefully we see this will be a lot easier to do. So it is very useful to get in the habit of trying to simplify things as much as possible. Again, for the sake of this quiz, if you get to here, you're good. I'd like to see you try and get further, but just go ahead and circle this answer before you start trying to make it any prettier. If you make any mistakes over here, I'm not going to count off points. I'm going to give full credit for this answer. I would like you to be able to get to that answer though, and I'm guessing on number 9 a similar type of thing would work on the test you're going to get. Finally, number 10, find the equation of the tangent line to the hyperbola x squared over 9 minus y squared over 4 equals 1 at the point 5, 8/3. Again, the equation of the tangent line requires me to find slope. Slope requires me to find a derivative. The current function is this. It is implicit in nature. I could make it explicit, but it's probably easy enough just to go with it as it is. I would multiply the entire thing times 36 though to get rid of the fraction. So if I do this whole thing times 36, 36 divided by 9 is 4 times x squared. 36 divided by 4 is 9 times negative y squared makes negative 9y squared. And 36 times 1 is 36. It's just easier to look at, fewer fractions. It's worth doing. Derivative of 4x squared is 8x. I'm differentiating x and nothing extra necessary. The derivative of 9y squared is 18y, but it's a derivative of y, so we're going to put dy dx, and that equals 0. Derivative of 36 is 0. So if I solve for dy dx, I'm going to move the 8x over here. I get dy over dx equals negative 8x on top and negative 18y on the bottom. Two negatives make a positive. 8 over 18 makes 4/9, so 4x over 9y will be the simplest derivative. Once I know what the derivative is, that allows me to find slope. Keep in mind x is 5, y is 8/3. Oh, that should say 9y on the bottom instead of 9x. So next I want to find slope. So if I just replace x with 5, y with 8/3, I'm going to get 4 times 5 on top, and 9 times 8/3 on the bottom. This 3 cancels that 9 down to a 3, so slope is equal to 20 over 24, better known as 5/6. So 5/6 is the slope. Point of tangency is 5, 8/3, so at this point I go to y equals mx plus b. Substitute everything I know in. Y is 8/3, slope is 5/6, x is 5, and b is what we don't know. 5/6 times 5 is 25 over 6. And since that's over 6, I want this to be over 6. Double both top and bottom, we get 16/6. Subtract 25/6 from both sides. We get negative 9/6 equals b, better known as negative 3/2. So slope is 5/6, y-intercept is negative 3/2. Y equals 5/6 x minus 3/2. Make sure the x looks like it's on top, or at least in front. Make sure it doesn't look like it's on the bottom. And that's the whole quiz. As always, study, prepare yourself for it, and look for the same types of shortcuts to occur on the quiz as happens on the study guide. Know your stuff well so you can finish this within the class period.